Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to give you an even deeper perspective of arithmetic with magnitudes and how what you learn to do with numbers in algebra comes to you directly from the arithmetic with magnitudes. So let's begin. Now, let's look very quickly at the big idea. Now, if you have any two ratios, such as you see here, a ratio of this dark blue line to this light blue line, or vice versa, or any one of the other 12 ratios that you can get out of intersecting two lines like this, and it doesn't matter how they're intersected, okay, no problem. Then you need to understand that at this stage, the ratios have no measure. They're simply distance magnitudes compared to each other. In other words, this ratio means compare the length of the dark blue line with the light blue line. Compare the length of the red line with the blue line, okay? So it doesn't matter how you write the ratio down. It's not actually a measure, right? So now, what happened in ancient Greece is that they moved away from this to finding a relationship for these four line segments, the green, dark and light blue and red. And there was a special relationship which basically says that if the endpoints of the line segments lie in the circle and the ratios are such that the two corresponding segments are collinear, then what we have is a relationship where we can define both division and multiplication, okay? And that's what actually happens. Why? Because in a circle, these distances, all these distances, have a special relationship. And that relationship is summarized by what you see here. The dark blue magnitude as a quotient with the red magnitude is the same as the quotient of the green magnitude with the light blue magnitude. And we know from a theorem in geometry that the angles in a triangle, if we join these dotted lines, so formed are subtended on the same arc. So these two angles here are subtended on this big arc, and this angle are subtended on this little arc here in pink. Okay, so we get to division and multiplication as follows. If we choose any of these line segments as a unit, it's not a problem. And we can show how division and multiplication work without any difference whatsoever. Let's suppose we choose this little green segment as the unit. And it doesn't have to be one unit exactly. It can be 2 units. It really doesn't matter at all. So if we do that, then we know that the product of these two lengths, of the dark blue and the light blue, gives us the length of the red line. And obviously this comes from the fact that the quotient of the red line, this red line, and this light blue line is the dark blue line, okay? And also the quotient of this red line with the dark blue line is the light blue line, okay? So both division and multiplication are defined geometrically for any two magnitudes. And note, we don't have to know anything about circles. Now, what this means is simply this. Division means that you can measure this red line with either of these, right? But now, if it's a simple case like 3, let's say it's got 3, a length of 3 here, a length of 2. It's very easy to see, right? Because we can just take this line and say, well, that's 1 and 2, and that gives us that line there, right? And similarly, we can say, use this length here, 2, to measure this one, which will give us the length of that line. However, if, suppose, we wanted to measure a slightly different line segment, say something like this. Let's say we've got that, and that's approximately equal to that magnitude known as pi, right? Now notice what happens. We cannot measure this line segment here because there's this little red part left over, but in geometry we do actually measure it, okay, because this little red part left over here happens to be an equal part of the unit. Okay, it happens to be an equal part of the unit that will fit exactly into the red line. And so how many equal parts of the unit do you think measure pi? And it doesn't have to be one unit. It can be any chosen unit you like. Well, it actually happens to be just over 7, by the way. So it doesn't matter what unit you choose. You can divide it up into equal parts so that it will measure pi. It's just that you simply will not be able to describe the measure of those parts. All I can tell you is that you will arrive at the conclusion that you'll need 7 and a little bit more of those parts to measure pi, okay? So now notice that both division and multiplication are defined geometrically for any two magnitudes, but this expression here, pi times square root 2, is not a number, it's a magnitude, okay? Pi means this length here, but there is no length, okay? There is no length. It's just a magnitude in geometry. And similarly, square root 2 would be described by the diagonal of a square, okay? And these two expressions here are not numbers, right? So what happens is, in Book 7 of Euclid's Elements, we transition to algebra where we introduce the number concept. So in geometry, pi is equal to the ratio of the circumference to the diameter. All that means is that you're comparing the two, right? But with the introduction of an abstract unit, we are a step towards denoting measure without caring about the actual size of the unit. So that's what the abstract unit is. It means a unit whose size is irrelevant, okay? And if we do that, we get to the fact that pi is approximately equal to 3, or 3.1, or 3.14, etc. But it says nothing about the actual measure of the antecedent part. It says nothing about this measure here, only an approximation, okay? Because any circle will produce the same equivalent ratio, right? So there are two other applets which I'll also give you a link to. It's this one here, which actually shows you that using the same idea, it doesn't matter which equivalent ratio you'll use, because the result, which you see on the left here, remains unchanged, right? So another applet that I showed you a long time ago actually tells you what is the quotient, okay? So it gives you a definition that will work for any particular number. So for example, if you say half times a half and 3 times 2, it will work exactly the same for both of those, because it comes from the geometry where that is exactly what happens. And I'll give you links to these. All you have to do is request a share to my applets folder, and you can have access to all these applets, and you can play around with them and see how they work. So what I wanted to show you here is that arithmetic, which came from geometry, was already defined with magnitudes, ratios of magnitudes, and gradually you came to all these operations. So for example, you learned rote fashion that P over Q plus or minus R over S is equal to this expression on the right here, right? You take a common denominator and you get what you have on the top. Similarly, if you take the quotient, you have PS over QR, and multiplication also with PR over QS. So you didn't really understand these, but all these actually come from this measure of ratios of magnitudes. Okay, so that's how we got them. They didn't just magically appear, and that's how they do work in geometry. Now, algebra, which is a weaker form of geometry, cannot handle every magnitude. So that's why we have approximations like 3.14 or 2.718, etc., whatever the case is. So much of the history of this is blurred as the arithmetic operators of geometry transition from operands that are magnitudes to ones that are numbers through the abstract unit whose size is irrelevant. So a quotient is really just a ratio that is measured by any two magnitudes which share a common measure or divisor. Now notice that if you have something like this, this here is a ratio of well, actually it's a proportion of equal magnitudes if both this length here and this length here are measured by the same divisor or unit. So it doesn't matter which way you look at it, that way or this way or any other way, right? To call this a number, to make this ratio transition to a number, both the red line and the blue line must have a common divisor or a common measure. And in that case, we can transition from writing 3:5 to 3/5, okay? It may happen that you have, as you're doing cancellation, 2/4 is equal to a half. And in geometry, these are not the same lengths because the antecedent in this case is 2, and in this case is 1. And 2 is not equal to 1. As you can see, 2 is not equal to 1. But as a ratio, they are equal because 2 is to 1 as 4 is to 2, right? And that's what is meant when you use the colon between the numbers. You're simply doing a comparison that is established on the basis of proportion, okay? So it's not enough to call 2/4 a quotient unless both 2 and 4 have a common divisor. So in the geometrical arithmetic operation, in order to say that the ratio P:(Q) is a quotient, means that both P and Q have a common divisor D, such that D and or equal parts of D measure both P and Q. So as you saw in the very first diagram that I gave you, this one here where we were trying to measure pi, or this magnitude which represents pi with a unit, we don't actually have a magnitude that is described by a number. In other words, it's approximately 7 parts with a little bit over, equal parts of the unit. 7 parts of the unit with a little bit, well, let me rephrase that. The equal parts of the unit are about 7 plus a very tiny magnitude that has no measure, okay? And that would be used to measure pi. So in that case, you would get the exact measure, right? Even though there's a little bit left over here, because in order for a number to measure both the large one and the small one, so in this case, you have the blue line and this little red line, this blue line and this tiny little red segment must have a common measure, okay? Which means that this unit must be divided into approximately 7 and a little portion that can't be measured. So I bet you didn't know that and have never thought of it. So there you have it. That's pretty much most of what you need to know. And of course, the product of two magnitude ratios is the quotient of either magnitude with the reciprocal of the other. And it should come as no surprise that multiplication is defined in terms of division. Now, I'm going to also give you a link to Euclid's Elements, a prologue to Euclid's Elements that gives you a complete systematic derivation of his 5 requirements, which are misinterpreted as axioms. It will also be available in this one link that you can request, this link over here, which will be in the details section. Well, I really need probably a few days, or more like a few weeks, to teach you this topic. And since nobody's ever going to invite me to do a TED Talk or anything else, this is about the best that you're going to get and the best that I can do, because I don't see myself writing another book on this topic, given my bad eyesight. So that's pretty much it. I hope you've enjoyed this little video. My name is John Gabriel. This is New Calculus Channel. And until next time, goodbye.